So by the way, how do you like the paper?
The paper was pretty interesting, and it is like giving an improvement to an already existing work has added a new research value, Professor. That seems to be like very interesting.
Yeah, I think if I remember correctly, I think this is the second paper on the image synthesis or image generation, right? Before we also have one paper presenting in this course, right? It's called something called giraffe, right? Giraffe.
Yeah.
Yeah.
Yes, Professor. So this is like GANs, it is 2D, and the giraffe they presented was the 3D. So that is like even more efficient than the GAN.
Yeah. The giraffe is still based on GAN, right? But this paper seems to be a different model instead, right? Yeah.
Yeah, Professor.
Okay, so we can see how this paper is like, and we can wait for a few minutes, and the student will join us. Yeah.
Sure, Professor. Let me slide share.
So by the way, how to pronounce your name? Your first name is Manisha, right?
Manisha, Professor. Yes, you did right.
How about your last name?
It's Suresh.
Suresh, right? You also have a middle name. Is Siri or it's not?
That belongs to the first name, Professor. So it is Manisha.
Oh, so it's not a middle name. I assume it's a middle name. So Manisha, Siri, Suresh, right?
Yes, Professor. So first name is Manisha Sri and the last name is Suresh.
Okay, I see. So by the way, for the screen you share with us, it seems I can see 2 pages. I can see both the current page and also the next page.
It's time, Professor. Let me check.
I assume you use two monitors or one monitor?
It's the one monitor. Is it fine now, Professor?
I think, yeah, this one is good.
Okay.
This one is good.
Yeah.
Okay. So the time is up and we can start. Hello everyone. So today we will discuss another paper on image and vision. By the way, this is also the last paper we have for this course on image and vision. And today we will discuss the paper title is called Diffusion Models Beat GANs on image synthesis. And the presenter will be Manisha Suresh, right? And so she will need a discussion with us and we can see how this paper is like. So Manisha, I can give the time to you and you can start when you're ready.
Yeah, thank you, Professor. Hello, everyone. Today I'm here to present a paper that is Diffusion Models Beat GAN on image synthesis by Prafulla Dariwal and Alex Nicole of OpenAI. Isn't the title sound interesting? So what does the paper do? Let's first go with the problem description. In this paper, the authors show that we can achieve the state-of-the-art image generation quality using a class of generative models called diffusion models, surpassing the state-of-the-art GANs on various sample quality metrics. Each of these images on the screen that you see here is a fully novel image generated by the proposed model after learning from the real images. As you can see that they are extremely realistic and diverse. So this paper tells us how the authors were able to achieve this with the diffusion models. So these generated image from a new class of model has been pushed to the point where the images they produce come to expect from the latest GAN models. But also they are better in the standard metrics we use to evaluate GANs, especially in this paper, they have used the Pratchett inception distance, which we'll be going through in detail about that in the upcoming slides. And overall, in this paper, the authors are mainly focused about improvements to this new class of model, and they call it as the diffusion model. To begin, let me introduce the basic problem of generative models. Let's say we have this data set of images of dogs, ostrich, and the goldfish, and we start the and we want to train a model that can generate new images of the same kind for us. So we start the data set of these real pairs that you see in the left, for example. So those are the real pairs of example, say X1, Y1, X2, Y2, and so on. So the X represents the images and the Y are the optional labels for them. A generative model tries to learn on how to generate a reasonable X given Y by trying to model the distribution, and they call it as like P of X given Y. Once trained, you can generate like the novel samples from the generative model, which you can see on the right. Over the past few years, generative models have gained the ability to generate human-like natural language, infinite high-quality synthetic images, and highly diverse human speech and music. And these models can be used in a variety of ways, such as generating image from text prompts or learning useful feature representations. While these models are already capable of producing realistic images and sound, there is still a room left for the improvement beyond the current state of art. And said that the better generative models could have wide-ranging impacts on like the various applications such as graphic, games, music, and countless like the other fields. To measure how well the generative model has learned to do this task, there is like few metrics that can be used. And in this paper, the most commonly used sample quality metric for image correlate with the human judgment. So in this paper, they mainly focus on the Frechet inception distance, or the FID. So this is a metric that calculates the distance between the feature metrics calculated for the real and the generated images. It's calculated by running images through a popular neural network like Inception V3 and calculated features for all your real images and generated images, and measuring how far these distributions are from each other. As an additional metric for comparison, past works uses the precision as a proxy for the fidelity and recall as a proxy for the diversity. So recall, which is like the synonym of the diversity, it is basically how many correct hits were found, and the precision is like how many of the found were like the correct hits. So it's basically the definition. So prior to our work, GANs like Big GANs, Style GAN 2 achieved the best image generation quality as mentioned by the FID, especially in most of the challenging datasets like the ImageNet. However, can suffer from issues like mode collapse, where they ignore how to model the part of the distribution and goes to get low recall. So this mode collapse happens when the generator maps the latent space to the same output, producing the high quality with very low diversity. That is
Uh,
like,
Hi, I have a small question. What is
sure.
FID? I mean, can you just explain that? Sorry.
Yeah, I'll be going through that in the later. Like it is a metric that is used to calculate the how far the distribution of the real image and the generated images are.
Thanks.
Any other questions till now? Okay. So mode collapse happens when the generator maps the latent space to the same output, producing high quality outputs with very low diversity. So that is when the generator producing the same images with a high resolution similar to that of the real data. So GANs are hard to train the stability because the adversarial training loss is non-stationary, meaning the data keeps varying with the time. For example, if you take like if you want to calculate based on the neighborhood, some of the data, then the neighborhood, it keeps on changing depending on the people and the circumstances. So that is what does non-stationary mean. So that makes it challenging to scale them. So basically GANs are like very hard to train the stability. Let's see like how the principle of the diffusion models and the GANs differ. In brief, this is how the generated model of GAN and diffusion model look like. The most significant common thing between them is that these models are like capable of generating the novel images from the noise. So let's dive deeper in the upcoming slides to clearly understand the GAN model and the diffusion model and how this diffusion model beat GAN. So first we have generative adversarial network or short GANs. As said, they generate images from noise, much like diffusion model. So we have this generator neural network starting from a noise Z that is shown here. or from some information, some informative conditional variable like class label, or you can also use it encoding, and it generates something that should look like a realistic image. So the success of this generator is rated by the discriminator, who labels the image as being either a true image coming from the training set or a fake one synthesized by the generator. So a GAN is based on two neural networks working against each other. So that's the name adversarial. But also it does that in a self-supervised learning. So this means that the data is not annotated, and the model creates its own annotation and it learns from them. The only thing we need is raw data, like bare text, if you wanted to do a natural language processing, or it can be images in case, like if you use like the computer vision. These samples we call real because these images are from the real data. But for GAN, we also need some fake data that comes from the discriminator. So discriminator is a neural network with the architecture of our choice. So it can be just fully connected layers with a sigmoid for binary classification at the end. The discriminator, what it does is like it has to predict whether the image that is being passed to it is real or it is fake. If it is fake, it is basically if it is coming from some other set of data. Well, so the some other data that comes from the second neural network called the generator. So the generator is also a neural network of our choice, because however it looks like it has to generate these fake samples. So this is in many cases just some noise variables in this called latent space that the generator produces samples from. But how? If we remember like how neural networks work, we know how much isn't there in that parameters. So the generator takes one number from the latent space, multiplies it with a parameter, and it does a mathematical calculation, and it passes through a nonlinear activation function, and it is the same process for like all the layers. Let's say, for example, if you want to generate a picture of a cat, the generator learns the right parameters to multiply the latent space in order to generate the grass pixels for the background of the cat. So the grass pixels are nothing but the values they have, like for each color, they have like specific RGB value. And this would be the ideal case, but of course, at the beginning, it would generate only noise from noise. So how does the generator learn to produce the grass or cats? So it has to take the feedback from the discriminator. So the discriminator job is like knowing from which image pool the input is coming from, and it has to predict if the image is coming from the real data or from the generator. If it succeeds to tell pictures apart, the discriminator has won. So if the discriminator predicts an image coming from the generator as being real, then it has lost and the generator has won. So this is a kind of, the adversarial gaming between the generator and the discriminator in the GAN. So depending on the error the discriminator makes, the parameters of the discriminator are updated in order to perform better next time. So every time the discriminator gives a prediction for a picture of the generator to be whether it's real or fake, the generator uses this feedback in back propagation to update its weight and perform like even more better until the generator is producing images of such quality. Because in practice, GANs are like notoriously difficult to train to conversions. It is like it is not like very impossible, but it is very hard. So it only works if the discriminator and the generator learn together and grow in competence at the same rate. I have just explained about the GAN initially to give you a clear picture like how this diffusion model beat GANs. So that would be like more clear when we go further. And so this is how all about like how GANs work. Let's go to the diffusion models. So however, like in like last couple of years, a very different class of generative models called diffusion models. Or alternatively, there's like some other models which like have just looked into, that is the score matching based models. They have like impressive sample quality on various image generative modeling tasks. So how do these diffusion models work? So it is like we take the image, and during the forward diffusion process, which is the orange on the orange arrow that is marked at the top, So during the forward diffusion process, we add a certain amount of noise. We store the noisier image and go on to generate the new image in the sequence by adding a little bit noise. And we do a certain number of steps. So if we do this like infinitely many times, we get an image that is just noise, but this infinity is something that only mathematics can deal with. So in reality, they do this like in like 100 to 200 times to get a last image that is like good approximation for the noise. So here is where it becomes interesting, like how can we generate these images with this thing? So we take a neural network and learn to reverse this diffusion process. So which is the green one. So the backward diffusion process involves the same network, the same weights to generate the image from t to t minus 1. So say t is the end and t minus 1 is the previous image that is generated at time t minus 1. To simplify the problem even further, one could choose to predict the noise at each step, which needs to be subtracted from the image instead of letting the network to predict the image. So this is just for the simplicity. In any case, the choice of the architecture of the neural network must be such that it preserves the data dimensionality. So they have considered a unit architecture, so which is a convolutional based neural network that is downsampling an image into a lower dimensional representation and reconstructs it during the upsampling. So the downsampling and the upsampling, these stacks communicate with each other through skip connections. And the unit is used in this paper, and they also use the global attention in the lower resolution layer. So this is more about the improvement in the architecture. While GANs are like capable of producing the photorealistic images, diffusion models are even better at realism. So when converting the when reverting the image from the noise by going through iterations and iterations of denoising, there is only a little room to deviate from the actual thing. So the generation process runs through all the checkpoints at each step more and more, and the details can be added into the image at each step. So this was just nice like the beginning, much like the GANs, but the diffusion models are like ridiculously faithful to the image data. So in brief, diffusion models work by setting up the problem of generation as the iterative denoising. They start with the forward process, say Q, and that generally adds noise to data at zero, destroying information at every end and only leaving us like pure noise as you see in the right, at step t giving us xt. So that's the sample xt. Say Q is adding small amount of Gaussian noise here. So by the end, they will have just something that is like the pure Gaussian noise. They then learn a model to reverse this process, that is like obtain a slightly less noised image from a more noised one. So now they generate a novel image. They run the whole process backwards from the pure Gaussian noise. So they iterate to denoise again at every step to get a novel image. The main training objective of this model is denoising, that is maximize the likelihood of the unnoised image given the image which is the noised one. So this is all about like how the diffusion models work. So let's see like what are the advantages of the diffusion models. So compared to GAN, as diffusion models are likelihood based models, they don't suffer from issues like mode collapse and are like stable to train and scale because they have the stationary object, which I said like it's opposite of the non-stationary, which I said before, and like other likelihood based models like the autoregressive models. So what happens in like the autoregressive models is like their sample can also provide much better fidelity, and they require like fewer sequential steps, making sampling reasonably fast. While GANs hold the state of the art, the drawbacks make them difficult to scale and apply to new domains. As a result, much work has been done to achieve GAN-like sample quality with the likelihood-based models. While these models capture much more diversity and are like typically easier to scale and train than GANs, the autoregressive models still fall in short of, in terms of visual sample quality. So diffusion models improve the reliability with increased compute and can produce high quality samples even on the most difficult ImageNet dataset using the upsampling stack. So however, The FID of this is still not competitive with the big GAN deep, the current state of the art on this data set. So in this paper, the authors are like mainly focused on the improvements over the amazing prior work they have done. So that is like the paper, which I have just mentioned that in the reference at the end of the section. So that is like the paper on denoising process. And that they say that the diffusion models could finally beat GANs in all this task. Next, we'll look at the background definition to provide a brief overview on of diffusion models. So what are the background improvements? So on a high level, diffusion model sampled from a distribution by reversing a gradual noising process. So in particular, the sampling starts with noise xt, and as I said, it produces gradually less noisy samples until it reaches a final sample. At each time step peak that corresponds to a certain noise level, and xt can be thought of as a mixture of signal. Authors assume that a noise is drawn from the Gaussian distribution. So that works well for the natural images and simplifies the various derivations. And diffusion model learns to produce a slightly more denoised image xt-1 from xt. The training objective is then, they say, it's a mean squared error between the true noise and the predicted noise. So they have just took the background definition of some of the mathematical related such as the mean squared error, variance, which I'll be like going through each of them on the later slide. So the researchers know that the training with this objective and using this corresponding sampling procedure is equivalent to denoising the score matching model used to sample from denoise model. So that are like trained with multiple noise levels to produce the high quality images. So there are like several recent papers that have proposed the improvements to the diffusion models and found that the fixing the variance to a constant is suboptimal for sampling with fewer diffusion steps. Another work proposed the DDIM, which formulates an alternative noising process that has like the same marginals on the DDPM. So we're producing like different reverse samples by changing the variance of the noise. So these are some improvements in the model that led to the improved FID, and find that they provide this as an alternate way to sample with like few steps and with a high sample quality. The researchers performed quantitative evaluations for comparing the sample quality across model quantitative evaluations, and they did using some of the metrics. While these metrics are often used in practice and they correspond well with the human judgment, they are not a perfect proxy, and finding the metrics for sample quality evaluation is still an open problem. So they just believe that. And there's like the metric inception score that was proposed by the earlier works to measure like how well a model captures the distribution while still producing the individual samples of a single class. But one drawback of this inception score metric is that it does not cover the entire distribution, or it doesn't give a well diverse image within a class. So they showed like they still have the data set that led to the higher inception score value. So to better capture the diversity than the inception score, they use the Frechet inception distance that was proposed, which is like more consistent with the human judgment than the inception score. So this FID provides a symmetric measure of the distance between two image distribution. And there's also the SFID that was proposed as a version of the FID that uses like the spatial features rather than the standard pooled features, and find that this matrix can capture like better spatial relationships dividing image distributions with a high level structure. Finally, they have also defined like they also had some definitions on the background related to the precision and the recall. So this is used to separately measure sample fidelity as a fraction of model samples which fall into the data precision, and diversity as a fraction of samples which fall into the sample recall. So authors use like the FID as the default metric for measuring the overall sample quality, as like it captures both the diversity and fidelity, and has seen that this is a standard metric for the state-of-art generative modeling work. So they use the precision or the inception score to measure the fidelity, and recall to measure the diversity or the distribution coverage. So in this paper, they have used these certain types of definitions that's taken from the background work. So the ideas is like the author hypothesized the gap between the diffusion models and the GAN by like two factors. First, they came with a design to give a better architecture for the diffusion models through like through a bunch of ablutions, and this improves our FID enough to obtain the state-of-the-art results for the unconditioned generation. So for the class conditional generation, author uses a technique called classifier guidance, where they train a classifier to classify the noised images and then take its gradient with respect to the target label, that is the Y, as a guiding signal during this sampling process. So this increases the probability that are sampled from a target class. They show that they can scale the gradients up to trade off the diversity for fidelity, and they see that they greatly benefit the conditional models, giving a state-of-art reasons. And with these improvements, the proposed model achieves a new state-of-art, surpassing the GANs on several different metrics and the data sets. So let's begin with the architecture improvements. So as observed by like the other works, inductive bias of architectures like UNIT improve the sample quality of diffusion models over the previous architecture. So the UNIT architecture uses stack of residual layers and downsampling convolution, followed by a stack of residual layers with upsampling convolutions. With skip, they have like the communication between the downsampling and the upsampling is done using skip connections that is between them with some kind of spatial size. So they start with the UNIT from the data, and they ablate the architecture in various ways. So here you could see like they made the byte length deeper, increase the number of attention heads, and they read more attention resolutions and use the big and style or residual blocks during the upsample and the downsample. And another technique for introducing the conditional information to the residual blocks, which we call like the adaptive group normalization, is mentioned in this paper. Like they observe that that is taken, there isn't any change that is done with respect to the layer, that's the convolution layer. They just observed that the previous works has given the improved FID with this adaptive group normalization, so they just used it. So in depth, next authors visit a technique called like the classifier guidance, as I mentioned before, to more strongly incorporate the conditioning information with the sampling process of these models. So they train the classifier of Y, which is the label of the image, given the sample, which is the XT, to predict the label Y for given noisy image XT. So then the sampling time, they take the gradient of the classifier and add it to the mean of the denoising stuff. It's kind of, steering the direction of the denoiser towards the gradients, that's increasing the likelihood to get a correct classification from the generated sample. They also multiply this gradient. They do the increase and decrease the amount of gradient scale. So they observe that using the higher scale helps the unconditional models focus more on the modes of the distribution and observe, and obtain the more realistic sample. Furthermore, they observe that the guidance can be used on top of the conditional models, and the authors review two ways of deriving the conditional sampling process using classifiers, and describe the use of such classifiers to improve the sample quality. So here the authors start with a diffusion model with an unconditional reverse noising process, and predicts the previous timestamp XT from like the XT plus 1. And this is using a Gaussian distribution, as you can see in the slide, in 0, 1. So 0 means it's like kind of the Gaussian process. And in this case, it gives the image that this came from. So where the previous image came from, the actual noisy image. So it's kind of, distribution of images where they came from. And again, they say that this model is Gaussian, and then the neural network will produce the mean and covariance given the image. So the mean is the mu denoted here, and the covariance is the sigma theta of xt, which you can see here. So the neural network is supposed to look at the image and decide what's the Gaussian distribution of these images and where this exactly came from. So this is a strong assumption that is adequately modeled as a Gaussian distribution, because they make like very small steps. They can train a neural network to do it in one step, but that is what is like the GANs result in. But this is like kind of using the distributional semantics. If you wanted to model the reverse as a normal distribution, is not true if we like take large step, right? So it is like if we take very tiny steps, we can adequately make sort of the argument that the normal distribution is kind of okay for this to work. And of course, it even makes them easier, so that they need the tiny steps, because in the tiny steps they are able to do the sort of modeling assumptions, and it works better. So in this conditional reverse processing, instead of simply reverting the process, which should be like part right, if the label is provided for that image, so if the label here it is y, so if the label is provided for that image, we can tell what class that image is from. So that can even give you a better job. So this is from the normal distribution, and they also like use the normalization constant C, which is like they have done the log thing. So that can be ignored to minimize the function. So so here, if you see here, like in this case, you have the predicted, so this is the predicted mean right here. They say that where this probability came from, given that I have a noise and a gradient with respect to the input. So if we make it a little bit, say if we make a little bit, it becomes much more likely under the class, and given that what the class label is, it becomes more accurate. So if given a mean, it becomes even more accurate to tell like where this image came from. So authors also go into this DTIM models, which are like different class of models very close there. So they use a score-based conditioning trick adapted from these other papers, which leverages the connection between the diffusion models and score matching models. So you can use that kind of actually get rid of noise in the system. So when we model the mean, we don't model the mean directly. So we actually model the noise, which is equivalent, but it works better from a neural network standpoint, and directly predict the predecessor. So we'll end up formally with a correct thing, and they don't have to sample as much as like so many steps. They can do it with a few number of steps, like say 12 steps in the reverse process. So they also use a discover hyperparameter. They observe that the classifier guidance are in log scale. So technically, the multiplication, it becomes an exponent with the log. So that simply means that the distribution is going to be more and more defined, depending on the type of hyperparameter they used. So the sample quality becomes higher. So let's now discuss about the evaluation part. This gives like the clear picture on the improvements they have done. So when we upgraded the architectural changes on a measure of 128/128, authors found that the improved FID almost like 2 to 3 points over the baseline models, which you can like see here. And when they next, the table of this ablation of various attention configuration indicate that more heads or fewer channels per head improves the FID. So these are all the changes that is related to the improvements in the architecture. So when evaluating the FID as a function of the clock time, the authors analyzed that the increased depth helped the performance to be better. So it increases the training time and takes longer to reach the same performance as a wider model, and hence decided not to use this change in their experiments. The authors further decided that 64 channels is best for the wall clock time and opted to use 64 channels per head as the default, and said that this choice also better matches the modern transformer architecture, and they are in line with the other configuration in terms of the final FID. So here you can see the 64 head channels that is marked in brown. So within the, it's like within the, it takes the less amount of time. So this is the kind of they see the improvement in the FID as function of the wall clock time. And authors experimented with a layer, so which I earlier mentioned, the adaptive group normalization. So that this incorporates the time step and the class embedding into each residual block after a group normalization operation is performed inside the architecture. And already the previous works have seen that using this layer has improved the FID. So the authors decided to use this throughout the work and also observe that this improved the FID. So in the here you could see like the improvement in the FID using this adaptive group normalization. So authors experimented with unconditional ImageNet models and found it is necessary to scale the classifier gradients by a constant factor that is larger than 1. In other words, authors observed that the distribution becomes sharper as using a larger gradient scale focuses more on the modes of the classifier, which is potentially desirable for producing higher fidelity, that is like, but with less diverse samples. So the table regarding the effect of the classifier guidance on sample quality shows that the sample quality of both unconditional and the conditional models can be greatly improved by using the classifier guidance. So with a high enough scale, the guided unconditional model can get quite close to the FID of the unguided conditional model. So the table shows that the classifier guidance improves the precision at the cost of recall, and thus it introduces the trade-off in the sample fidelity versus the diversity. In this, the authors observe that when we increase the classifier grade and scale, we obtain like a smooth precision, which measures the precision is nothing but it is the fidelity, that is like how many found were how many of them found that is proved to be correct. So correct hits, and the sample. So the authors observe that when we increase the classifier grade and scale, there is a smooth increasing precision which measures the fidelity, and or how the sample is realistic at the cost of recall. So authors find that a scale of 1 or 2 is actually best for the FID, but they also mention that we can obtain like the more realistic sample by increasing the scale to a higher value. So authors computed the similar trade-off curve between the big GAN deep by varying its truncation factor, and found that the guidance works better than the truncation, keeping a high recall and gets much better FID. So here you could see like the classified guidance that the diffusion models use have like the better FID than compared to the big GAN deep. And you could see like in this case, it's like the guidance works better, keeping a high recall than the big GAN deep. So this is like kind of like everything put together. So Finally, the authors made a thorough comparison with past image generative models using all the sample quality metrics. And on conditional image generation, the model achieves the state of art results on Elson, which is like bolded here. It showed better results on Elson than GANs without the improved architecture. And similarly, on conditional generation on ImageNet, it's really hard time due to its immense diversity. Diffusion models beat the big GAN deep and achieves the state-of-art results using their classified guidance while having like very higher recall. And the authors found that they can also obtain the competitive sample quality by using like few number of steps. So that here they have just used the 25 sampling steps and observe the higher sample quality. So we can here see that the proposed model have a higher recall than GANs and cover much more of the models which you usually see in the sample grid. So on the left are the samples from the big GAN deep. The middle column is the proposed model, diffusion model, and right mode is the actual real data. So for the big GAN deep, you can see like all the flamingos samples look similar, whereas our model generates samples with like very specific viewpoints. And here you can see like how many number of flamingos are available. So authors also evaluated the compute requirements of the model and produced that the models can achieve a better sample quality when using the same amount of training compute. So the authors found that they can improve the sample quality of further combining the guidance with the sampling stack. So while upsampling improves the precision while keeping a higher recall, guidance provides a knob to trade off the diversity for much higher recall. So authors achieve the best FID by using a guidance at a lower resolution before upsampling to a higher resolution. So they can see like they have got the FID value of 3.94 and 3.85 respectively on the ImageNet 256 and 512, leading to more photorealistic sample by some of the classes seen right here. So some of the related works are score-based generative models for modeling data distribution. Using these gradients improve the sample quality. And there are like diffusion-related models for learning a model with learned iterative generation steps and achieve good image samples with a likelihood objective. And GAN that introduce the truncation trick to trade off the diversity for fidelity. So there are like other works that have control generative models with a pre-trained classifier, and there are works that are related to the likelihood-based models to produce a high fidelity image samples using the classifier rejection. So these are some related works to the proposed paper. Let's now look at the limitations and the future work. So while the paper believes that the results are an existing data point for generative modeling using the future models, there are still some important limitations that needs to be addressed. So in this paper, the authors have like well provided the limitations and they also said like what can be done towards the future work. So this is this I could see as like the strength of the paper, because most of the papers doesn't directly straightforward the limitations. So they said like sampling from this models are still much slower than big GAN because the architecture is huge and it requires like more sampling steps for the future. And the guidance can be used like for the conditional task. So which is like since till now the classifier guidance is basically it is used on condition tasks. So in the future they said like they can work on like the unconditioned task. Still, the authors believe that these models are like extremely promising, and we like they say that they are looking like to for the future work to overcome all these limitations. So in summary of this paper, it's like the quick overall conclusion, like what the paper is on. So the authors prove that the diffusion models, a class of likelihood-based models with a stationary training objective, can obtain like better sample quality than the state-of-the-art GANs. And the improved architecture is like sufficient to achieve this on unconditional image generation task. And the classifier guidance technique is used on the class conditional task. So the result, the authors found that the scale of the classifier gradients can be adjusted to trade off the diversity for the fidelity. These guided diffusion models can reduce the sampling time gap between the GANs and the diffusion models. So finally, by combining the guidance with upsampling, it is said that the models can further improve sample quality and high resolution conditional image synthesis. So finally, the references are here. So this is the paper citation with its link in its archive website. And below is the link for the code base of this model that is provided by the authors themselves in GitHub. And these are the other resources that can be referenced. Thank you. Any questions?
Okay, so the talk is very good. Any questions? I can see some question in the chat. Maybe Manisha, you can have answer the question in the chat as well.
Yep. So what is FID? FID is a metric they use to see how the distribution between the real and the generated images are. In text generation, what does noise mean? Can you just unmute and let me know like what it is? I couldn't get that. Arifa?
Yeah, Rifa, maybe you can elaborate more for your question on the text generation for the noise.
Yeah, I can go like with slide.
Rifa, are you online or not? Maybe you can say more for your question. Right?
Okay, maybe I can go to the next question.
Yeah, maybe we can go to the next one.
So interesting. The lesser the FID, the better the model is. Yes, lesser the FID, it means that the model is better. Yeah, you found that correct. Yes, the diffusion noise is Gaussian here, and in GANs, it's mostly random. What is the boundary values for the scale, Y scale from 1 to 10? So they have experimented by scaling, by scaling the gradients on like the ImageNet data set. And as I show, like I can show you here. So they have done this kind of gradient scale and they found like what smoothly gives the better diversity or the fidelity, and they have just scaled to a small number of, but still they have mentioned that in the paper that the scaling can be increased to get like even more better sample qualities. Is the main benefit of diffusion model compared to GAN the added diversity we get in the images? In this paper, they mostly specify like they get the better sample quality, so which in turn means like the diversity. I hope I've answered all the questions.
Yeah, so any more questions? I hope the student you are still, I mean, you're not lost, right? I mean, you can follow us, right, for the paper, for the talk. Do we have any more questions? By the way, I hope you read the paper before class, right? Because many of the questions I can see, we can see the content in the paper actually. And for scaling, the all the mentioned scaling in section 4.3, right? I mean, so if you read the paper, you should know the scaling actually. Yeah. Any more questions from the students? Oh, if you have no question, then probably that's it for today. Oh, anyway, thank you so much, Manisha, and for the talk. The talk is very good, and it generally cover all the materials in this paper. Yeah. So for the student, if you have any more questions, please let us know. I mean, we still have lots of time. And this paper is the second paper on image synthesis or image generation, actually. Before we have another paper, the presenter is Joe Henry. We present another paper on image generation, actually. And this is the second one, and this one is very different. Before the model is on GAN, however, this model is based on a diffusion model, or it is more like a probabilistic models, actually. Yeah. So by the way, this is also the last paper we have for image and vision. And next week we'll move to the graph neural nets. And this will be a new topic. And I hope you read the paper before class, then you will be able to follow us. By the way, if you don't read paper, just attend a talk, you can get notes very easily because the talk can be very high level, right? Then you have to read paper, then you can learn something useful, right? And also in the paper, you can see some new concepts, new terms, or new technology. My suggestion, you can also refer to this kinds of paper side as well. Then you can learn something more, right? Beside the paper we cover in the schedule spreadsheet. You know, I mean, if you want to do research, you have to learn new things all the time, right? And you cannot wait until, I mean, the presenter tells you the answer, right? You cannot seek for the answer by yourself as well. Then you can learn something, learn more and also learn faster than the others. So keep learning, keep reading, right? So it is important, it is a necessary process for learning, right? New stuff. I mean, by reading papers. Anyway, so the talk is very good. Thank you so much, Manisha, for the talk. And that's it for today. Yeah, thanks.
Thank you, Professor. Thank you, everyone.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Okay, thanks, Manisha. Thanks.
Okay,
Bye-bye.
Professor. Thank you so much.